Section 6.4 is transformations on exponential and logarithmic functions. So transformations on exponential and log functions work the same way pretty much as the other transformations that we've learned about this year. So for horizontal translations, we're taking that h value away from our input or away from x. So we have f of x minus h. For our vertical translation, we're adding that k value, that constant, after the function. So f of x plus k, kind of adding to the output of the function. And then for a reflection, it's negative f of x for a reflection in the x-axis, or f of negative x for a reflection in the y-axis. And then a vertical stretch or a shrink means that we're taking a scale factor or constant and multiplying it throughout our entire function. So for example 1, describe the transformation of f of x equals 2 to the x power, represented by g of x equals 2 to the x minus 3 plus 1, then graph each function. So up here with g of x, we're taking 3 away from x. So that means that h is equal to 3 because there's already that negative embedded in there. So we're going to go right 3 because h is positive 3. And then this 1 added after is telling us that we need to go up 1. But we're just going to make a table for the parent function and then do the transformations after once we have those points. So for f of x equals 2 to the x power. And one thing to know about with exponentials is parent functions may look different depending on the problem. There's no one set parent function, but it's basically our base raised to the x power without any other transformations, but the base can change depending on the problem. So I'm going to choose x equals negative 1, 0, and 1 for my exponential. So when I make x equals negative 1, when I raise 2 to the negative first power, that's 1/2. When I raise 2 to the 0 power, that's 1. And when I raise 2 to the first power, that's 2. So we can plot those points, negative 1, 1/2, 0, 1, and then 1, 2. And then we can connect those points. And that is f of x, our parent function. So for g of x, we know that g of x is f of x just translated right 3 up 1. And then so we can just count off each of these points right 3 up 1. So from negative 1, 1/2, if I go right 3, I go right 1, 2, 3 over to 2, 1/2, and then up 1 to 2, 1.5, or 2, 3/2. And then 0, 1, if I go right 3, I'm at 1, 2, 3, 3, 1. And then up 1 to 3, 2. And then for 1, 2, if I go right 3, 1, 2, 3, I'm over at 4, 2, and then up 1, 2, 4, 3. And then we can connect those points. So one thing that you have to keep in mind for an exponential is all exponentials have a horizontal asymptote. So the parent function has one at y equals 0. Since this graph has been shifted up 1, g of x has a horizontal asymptote at y equals 1. So this is our g of x. So just for practice, we'll state domain and range and asymptote for just g of x. So I'm going to start backwards. I'm going to start with the asymptote. So since for the parent function, the asymptote is at y equals 0, if the g of x is being shifted up 1, then the horizontal asymptote shifts up 1 to y equals 1. And then that means for range, that means that this line is going to get infinitely close to my horizontal asymptote, but it's never going to cross it. So the range on my y-coordinates are limited to being above the horizontal asymptote. So my range would have to be y is greater than 1. So because there's an asymptote at y equals 1, that means that y can never be equal to 1, and it'll also never cross 1. So it'll never drop down into the y equals 0 and then negative y's. And then domain for exponential functions is all real numbers, because I can put any x value in and get a real number out, regardless of how big or how small it is. For example 2, describe the transformation of f of x equals e to the x, represented by g of x equals negative e raised to the x plus 6, and then graph each function. So we know that this negative out in front is a reflection. And the plus 6, or the x plus 6, is telling us that we have to go left 6. Because it's like x minus negative 6. So h is negative 6, so we're going left. So we're going to go, we're going to do a reflection in the x-axis. Since it's out in front of the function, it's not the x that's being negated. And then also translated left 6. So when we make a table, we'll make it for just the f of x. So x and f of x. And of course, f of x is e to the x. So since it's an exponential, we'll choose x equals -1, 0, and 1. So when I raise e to the negative first power, I get about 0.37. When I raise e to the 0 power, anything to the 0 power is 1. And when I raise e to the first power, I get about 2.72. So we can graph those original points, f of x, so -1.37, and just graph them as accurately as you can, and then 0, 1, and 1, 2.27. And that's our f of x. So when we go to graph our transformations, one thing you need to consider is whether or not the order is going to impact it. For this particular problem, it's not, but if it was, you would want to follow order of operations. So if you picture it in your head, if I do a reflection first, it reflects over and then moves to the left 6. If I move to the left 6 and then reflect after, it doesn't really change the actual outcome of the graph. But if it did, you would want to follow order of operations, and with it written right now, order of operations would tell us to move left 6 because that's the exponent, and then we'd be multiplying by a negative after. So we'll move left 6 first and then do the reflection in the x-axis. So if I want to move left 6, -1.37 is going to move over to -7.37. So 1, 2, 3, 4, 5, 6 over to -7, but the height doesn't change here. And then 0, 1 is going to move over to -6, 1. Again, the height's not changing, we're just changing the x-coordinate, we're shifting it left 6. And then 1, 2.72 is going to shift over to 5, 2.7, -5, 2.72. So these points are my graph being just translated to the left 6, and then if I want to reflect it after that, I just need to flip all of them over the x-axis. So reflection in the x-axis is I'm flipping over the x-axis. So -7.37 turns into -7, -0.37. And then -6, 1 turns into -6, -1. And -5, 2.72 turns into -5, -2.72. And then we can connect those points. So if we're figuring out domain, range, and asymptote for g of x, this graph hasn't really, we're going to go backwards again and start with asymptote. This graph hasn't really shifted up or down at all. So it has been reflected, but my original asymptote was at y equals 0. And then the graph shifted left, and then it reflected over that asymptote. But it didn't shift up or down, so the asymptote did not change, and it's y equals 0 still. And then for my range, since I'm limited with g of x to just going up to y equals 0, I can go down forever, but the highest I'll go up is just getting infinitely close to y equals 0 without actually ever crossing it or touching it. My range is y is less than 0. And then the domain for an exponential is going to be all real numbers. The graph extends in both directions for x. for example 3, graph f of x equals log base 1/2 of x. So for logs, if we make a table for f of x, remember with logs, the x values that we're going to pick are going to be the reciprocal of the base. So the reciprocal of 1/2 is 2. And then we're going to pick 1, and then we'll pick the base, 1/2. So when I plug in 2 for x, that becomes log base 1/2 of 2. So that's saying 1/2 to what power equals 2? Well, 1/2 to the negative first power equals 2. And then when x equals 1, log base 1/2 of 1, it's asking 1/2 to what power equals 1? Well, 1/2 to the 0 power equals 1. And then when x equals 1/2, becomes log base 1/2 of 1/2. It's saying 1/2 to what power equals 1/2? Well, 1/2 to the first power equals 1/2. So it's been consistent where with logs, if we plug in the reciprocal of the base, we get out -1. If we plug in 1, we get out 0. If we plug in the base, we get out 1. And we can graph those to -1, 1, 0, and 1/2, 1. So because exponentials and logs are inverses of each other, so we know with exponentials there's a horizontal asymptote, but logs that are inverses are reflections of each other over the line y equals x. So that means when the when all the points flip, so does the asymptote. So logs will have a vertical asymptote instead of a horizontal asymptote. So the parent function for any log graph will have a vertical asymptote at the line x equals 0. The only thing that will change it is if the graph shifts left or right. So our asymptote is x equals 0. So that means that our range is restricted now because the range is just all of the x coordinates. So my range is limited to the right side of my asymptote. That means that on this side, or on the right side, this line will get infinitely close to the y-axis or to the line x equals 0 without actually touching or crossing it. So my domain has to be x is greater than 0. And then range, just like domain for exponentials was all real numbers, range for logs will be all real numbers because this graph will extend in both directions for y forever. For the next example, graph g of x equals log base 3 of x. So if we make a table for g of x, we're graphing a log. So for our x values, we want to pick the reciprocal of the base, 1, and then the base. So 1/3, 1, and 3, since it's log with a base of 3. And then when we go to fill in our table, log base 3 of x becomes log base 3 of 1/3. So that's asking 3 to what power equals 1/3? Well, 3 to the negative first power equals 1/3. And then when x equals 1, log base 3 of 1, 3 to what power equals 1? 3 to the 0 power equals 1. And then when x equals 3, log base 3 of x, log base 3 of 3, 3 to what power equals 3? Well, 3 to the first power equals 3. So that'll stay consistent on whenever you're graphing logs for the parent function. We'll do the transformations after, but for your table for the parent functions, it'll be the reciprocal of the base, and then 1, and then the base. And if you do that, you'll always get out -1, 0, and 1. So when we go to graph it, 1/3, -1, 1, 0, and 3, 1. So we can connect those points knowing that there is a vertical asymptote now. This graph hasn't been shifted left or right at all, so the vertical asymptote is still x equals 0. That means that our graph will never cross the line x equals 0. So that means that there's going to be a domain restriction because the domain, all the x coordinates, can only be on this side, the right side of the asymptote. So if they have to be on the right side of the asymptote, the domain is restricted to x is greater than 0. And then the range for any log function is all real numbers, because that graph will extend in both directions of y forever. And then for example 4, 4a is f of x equals log base 3 of x minus 2 minus 1. So if normally we would take this function and we would just make a table for the parent function, which the parent function would be this function up here. So the log base 3 of x. It's the same thing, it just takes away the transformations, the right 2 from the minus 2 and the down 1 from the minus 1. So because we already have a table of those points, I'm just going to plot the points from this table down here, and then we'll do the transformations after. So my parent function would be that g of x equals log base 3 of x, and that's what we're going to graph first. So that table is up here. So 1/3, -1, 1, 0, and 3, 1. And then we're going to translate each of those points. Since it's x minus 2, we'll go right 2. And then since the minus 1 after, we'll go down 1. So for 1/3, -1, if I go right 2, I end up at 2 and 1/3, and then down 1, 2 and 1/3, -2. And then 1, 0, if I go right 2, I end up at 3, 0, and then down 1 at 3, -1. And then 3, 1, if I go right 2, I end up at 5, 1, and then down 1 to 5, 0. And then I can connect those points, just keeping in mind that if my graph has shifted right 2, so has that vertical asymptote. So it's no longer going to be at x equals 0, it's going to shift over here. So my line should never cross this point, or my graph should never cross that line. You can always draw the dashed line for the asymptote if you want to, you don't have to. But it's helpful sometimes for you to see where your graph should stop. So our graph is going to get infinitely close to this asymptote at x equals 2, but never cross it or never touch it. And the reason that asymptote is there is because for the parent function it's at x equals 0, but this graph has been shifted 2 to the right, so now it's at x equals 2. So our asymptote is at x equals 2. You can see that the domain of this graph is restricted to the right side of the asymptote. So our domain would be x is greater than 2 now, because it's cut off at 2. And then range would be all real numbers still. For b, f of x equals 3 times log base 1/4 of x minus 5. So we can see the different transformations here. We know that this is a stretch by 3 if I have that coefficient out in front. And then that minus 5 is telling us that we have to go down 5. So we can make a table for just the parent function. So it would be the original log with everything taken away. So we'll call the parent function g of x. So I'll make a table for x and g of x. And g of x is just going to be log base 1/4 of x. So that's what I mean by like the parent function will change depending on what the base of the log or the base of the exponential is. But the big thing is just that the different transformations are taken away. So if I make a table for log base 1/4 of x, I'm going to pick the reciprocal of the base, so 4, 1, and then the base, so 1/4. So then log base 1/4 of 4, it's saying 1/4 to what power equals 4, 1/4 to the negative first power equals 4. And then log base 1/4 of 1, 1/4 to what power equals 1, 1/4 to the 0 power, because anything to the 0 power equals 1. And then log base 1/4 of 1/4, 1/4 to what power equals 1/4, 1/4 to the first power. So that's still consistent. We put in the reciprocal of the base and we got out -1. We put in 1, we got out 0. We put in the base and we got out 1. So we can graph those points. So 4, -1. And then 1, 0, and 1/4, 1. And then this one does, but we're gonna go in order of, like, think order of operations again, like I said. So if we were to follow order of operations, we would multiply before we subtract. So we're going to do the stretch before the translation 5 units down. So I'm going to stretch each of these points. And the way that you stretch points on a graph is you just multiply the y coordinate because it's a vertical stretch. So we'll multiply the y coordinate by this number 3. So 1/4 1. If I multiply the y coordinate by 3, that becomes 1/4 3. So that moves up here. And then 1 0, if I multiply the y coordinate by 3, then the y coordinate is still 0. So that stays 1 0 because 0 times 3 is still 0. And then 4 -1, if I multiply the y coordinate by 3, it becomes 4 -3. So I have these 3 points now, and then I need to translate each of those points down 5. So 1/4 3, if I move down 5, is going to become 1/4 -2. And then 1 0, if I move down 5, is going to become 1 -5. And then that was 4 -3, so if I move down 5, I'm going to end up at 4 -8. So now I have these 3 points. Before you connect them, just think about where the asymptote would be. It was originally at x equals 0. The graph did not translate left or right at all, so it's still at x equals 0. So it's going to get infinitely close to the x-axis or the y-axis without ever actually crossing it. This graph just looks a little bit different because of how it's been stretched. So it'll get infinitely close to the x-axis without ever actually crossing it. And then it'll continue on forever in the downward direction. So for the domain range asymptote, for the asymptote, because there's no horizontal translations, the asymptote is still x equals 0, has not changed. And then because my graph is limited to the right side of the asymptote, my domain is x is greater than 0. And then range for logs is going to be all real numbers. That graph will extend in both directions forever for y. For example 5, write a rule for g that represents the indicated transformation of f. F for a, f of x is 3 raised to the x, and we want to do a reflection in the x-axis followed by a translation 2 units left. So if we're starting with f of x equals 3 to the x power, I know that a reflection in the x-axis, that's going to be negative f of x, and then followed by a translation 2 units left. That would mean that's like f of x minus or x plus 2, because h is -2. So to go left, we're adding 2 to x, and then if I want to, it's a little bit tricky with like the wording, because sometimes it makes you feel like you need to use parentheses like around the negative, but I'll call my translated function g of x. So if I write my reflection first, so negative x raised to the x power, I can't put the negative in parentheses because in order for it to be like an exponential function, it has to have a positive base. So having the negative out in front is all you need. If you put the negative in parentheses, it like ruins the function. It's no longer an exponential function, because if you think like if it's a negative number raised to a power, it's gonna like oscillate back and forth because the output's gonna become positive and negative. And then lastly, if I want to translate 2 units left, I just need to add 2 to x. So g of x equals -3 raised to the x plus 2 power. And then for b, f of x equals log base 1/6 of x, and we want to translate 1 unit down followed by a vertical stretch by a scale factor of 5. So translating 1 unit down, that would be f of x minus 1, because k would be -1. And then a vertical stretch by a factor of 5, that would be like 5 times f of x. So if we want to make sure that we do the translation first, we should do it in 2 steps. I'm going to call the middle step h of x. So h of x is going to be f of x translated 1 down. So it'll be log base 1/6 of x, and then to translate 1 down, we'll do minus 1. And then now that we have the translation 1 unit down, now we can put in the vertical stretch. So the final function will be g of x, and g of x is going to be h of x all multiplied by 5. So stretch by 5, it'll be 5 times log base 1/6 of x minus 1, and that whole h of x function needs to go in parentheses, or else the translation won't be included with the stretch. And then lastly, we just need to distribute the 5 in. So it ends up with g of x equals 5 times log base 1/6 of, I don't know why I included the parentheses. Anyways, 5 times log base 1/6 of x becomes 5 log base 1/6 of x, and then 5 times -1 becomes -5. So g of x equals 5 times log base 1/6 of x minus 5.